Okay, so maybe we should get started. All right. Okay. So last time we talked about some applications of the BCH formula. So remember, the BCH formula is really, a way to express e to the x, e to the y in a Lie group as some expression, e to the something, where that something comes from the Lie algebra. But it's a formal series. It's a series with infinitely many terms. Okay. And well, that formal series expression, which I had here, it can be proved, as we saw, using some integral form. So this is the form that we want to prove. And last time we studied some applications of this existence of this formula. So one application was that if you have a Lie algebra homomorphism from a Lie algebra G to a Lie algebra H, you can always lift it, at least locally, to a group homomorphism. So within a neighborhood of 0 in the Lie algebra and identity of the Lie algebra, you can use this exponential formula to define a map F, which is a local group homomorphism, which means that it satisfies this relation, but only if A, B, and AB are within small neighborhood of the identity element of the domain group G. Okay. So you cannot necessarily lift a Lie algebra homomorphism to a Lie group homomorphism, but at least locally you can do this. All right. And the idea was basically to use this power series to define, to verify by some trick, to verify that FAB equals FAFB, but using the fact that this power series is valid, it converges in some small neighborhood in the Lie algebra, okay? Some small neighborhood of the 0 element. The argument would not be valid for general X and Y because the convergence will be an issue, okay? And then as a consequence, we were able to show that if you have a Lie algebra homomorphism, well, okay, so we basically, okay, so there was like 2 steps. So, maybe the consequence which I wanted to state, did I state that consequence? Maybe not yet. But, well, basically, if you have a Lie algebra homomorphism, you are able to lift this Lie algebra homomorphism to a Lie group homomorphism whose derivative is the Lie algebra homomorphism, at least when G is simply connected. And the reason is that you can first lift this to a local homomorphism, and then you can show that your local homomorphism can be extended to a global homomorphism, to a homomorphism from the entire group. Okay, and that was basically the argument that we gave. Like, we kind of didn't finish, but I gave the main ideas of the argument. If you have a local homomorphism and your domain group is simply connected, if G is simply connected, and this F is a map from a U in G to F, so this F, this F goes from U to H, then you can extend this F to a group homomorphism, to a continuous group homomorphism from G to H. Okay? And the argument, what was the argument? The argument was, in order to define capital Phi of some arbitrary element G, what we do is we take a path in the Lie group G, which we know is simply connected. So in particular, it's connected, like it's path connected, and any loop shrinks. So you take any loop that connects the identity to G, and you define Phi of G incrementally by first defining it on subintervals here. So you define Phi of G by taking a subdivision of this path into small pieces, so that on each part you can justify how to define your map. And that was by this formula. The idea was that the ratio, so to speak, of gamma of 2 successive points on this path, this ratio lies within the small neighborhood of the identity in capital G. And therefore, you can use this F to define Phi. And now you have to show that this is a well-defined definition. You have to verify that the definition of Phi is independent of the choice of this path, independent of the subdivision that you take, and it also provides a group homomorphism. So last time I explained why it's independent of the path. And the reason is, I'm sorry, not the path, but just the subdivision. The reason is that, well, for 2 different subdivisions, you can take a refinement of both of them, which is the union of the points that subdivide, okay? You can, if you have two ways of subdividing, you can take the union of the points that subdivide, and you get some subdivision that's a refinement of both of the ones below. So now you show that by adding points in between 2 points in a subdivision, 2 successive points in a subdivision, this definition does not change the value. Okay, this definition of phi of g, it still produces the same value. And the reason was this simple cancellation argument. And if you add one more point, like this gamma of s, then you use the fact that this f is a local homomorphism to see that you could actually cancel the f of gamma of s and f of gamma s inverse. Okay. And the argument for showing that, I just want to remove the extra stuff, maybe. Okay, so the argument for showing that this definition is independent of the choice of the path was also by the fact that a deformation, like it's sort of the simply connectedness can be interpreted as you take two paths connecting the identity ng, you can deform one to get to the other. Okay, and this deformation would be like formally sort of a mathematically rigorous way. This is just a map from 0, 1 across 0, 1 to G, where at time 0, say when the second parameter is 0, you get the first path. At time 1, you get the other path. Okay. And then you could see that you could just do this like incremental steps, just like before, so that within a small square where a change in the path takes place, everything lies within some small neighborhood of identity in G. So the property that F is a local homomorphism in that neighborhood still justifies that the two paths which are different in this little square in terms of the way they're connecting 1 and G, the two paths give the same value for phi of G. Okay. And showing its group homomorphism is also essentially the same. And the book outlines some argument. Okay. But I mean, the argument, if you write the epsilon delta, it can be long. But this is one of those kinds of proofs that there's like two levels to understand it. There's sort of a conceptual level where you understand the big picture, what's going on. And then there's a second level where you want to write the details to make sure all the epsilons and deltas work out. But when you understand this at the top level, you basically are sure that at the next level it works. Okay, so the main thing is to understand why it works at the top level without writing the little details blindly. Okay. So was the explanation clear for this argument? Was it satisfactory? You have a question? Okay. All right. So now, all right, then maybe I should just strictly write this corollary that for simply connected domain, you can lift your homomorphism. So I didn't write it. This was a consequence of this assertion. Maybe I write it now. So then here is the theorem, continuing from the last lecture. Okay. So let G and H be matrix Lie groups. I mean, we said it in matrix Lie groups, but really everything can be modified. So this is true a statement about all Lie groups. Okay. So with Lie algebras, the corresponding Lie algebra is G and H. So let now phi from G to H be a Lie algebra homomorphism. Now assume that G is simply connected. As I mentioned, when we say simply connected, it also includes its path connected by some convention. So then there exists a unique Lie group homomorphism like capital phi from G to H such that the derived Lie algebra homomorphism is phi. Or equivalently, phi e to the x is e to the phi x. So what's the proof? So the proof is that from phi, so existence, let's talk about existence and then uniqueness. From phi, we can construct first a local homomorphism. We can always do this. It doesn't require simply connectedness. Homomorphism. Like UF, then by simply connectedness, I don't know, maybe I should say simple connectedness. Is that like grammatically? Yeah, or simply connectedness? What do you think? Okay, maybe simply connectedness. Okay, by simply connectedness. We can extend. I mean, we can find capital phi from G to H such that it's the restriction of capital phi to U is F. So this is the existence part. And now what about the uniqueness? So can you explain why this map should be unique? So suppose we are given two maps like phi 1 and phi 2 are two choices. Okay. Is this enough for saying that phi 1 equals phi 2 on the nose, like without doing any work? Well, not every element is an exponential, right? So we cannot say that this means phi 1 of G equals phi 2 of G for all G in the group because everything is an exponential. But everything is a product of exponentials. So we know that phi 1 of e to the x1, e to the xr equals phi 2 of e to the x1. I mean, well, maybe I should write what it is. It is like e to the... Both of these, like phi 1 and phi 2, we know they're group homomorphisms now. So this is e to the phi x1, e to the phi xr. And so this is equal to, by the second relation, is phi 2 of e to the x1. Phi 2 of e to the xr, which is phi 2 of e to the x1, e to the xr. Okay, so now every G in G is a product of exponentials. We have proved this before for any connected Lie group, right? And this means that phi 1 equals phi 2. All right, is it clear? Now, here's also another corollary, which is interesting and important to know. So if we have two simply connected Lie groups, and we know that their Lie algebras are isomorphic, then the two Lie groups are isomorphic. So why is this true? Can you explain? This should be a consequence of the previous statement. So why is it true? Right. Okay. So in both directions. So the proof is really simple. The proof is that, well, this map, so the map Okay, Lie group homomorphism. Okay, and the inverse map. Maybe I just called it phi. The inverse. So this also lifts to some psi. Now you have to show that these two maps are inverse to each other. They're isomorphisms. In particular, maybe it's enough to show that they're like inverse to each other. Why is that so?
By uniqueness, like that composition has to lift.
That's right. So now psi or phi, this is a map from G to G that corresponds to phi inverse O phi, which is the identity going from G to G, right? By uniqueness, capital phi should be, by uniqueness that we just proved, note that G is a simply connected Lie group. By uniqueness, we must have, because of course the identity map on G corresponds to this identity on the Lie algebra. So by uniqueness, this psi O phi, which corresponds to that identity map, should be the identity map. And similarly, because H is simply connected, phi O psi will also be the identity of H. Okay, so you have two group homomorphisms, they're inverse to each other, so they provide this isomorphism. Okay. So what does this mean conceptually now? It means that if you want to construct a Lie group corresponding to a Lie algebra, maybe we should go for this simply connected guy. We should try to show maybe that for any Lie algebra, there's a simply connected Lie group, because this guy is unique up to isomorphism, right? Now, this assertion, this implication of this corollary would not have been true. Oops. Did I close it? Too bad. This would not have been true if one of G or H was not simply connected. Can you give an example? Okay, I just would like to come back to this. Okay. All right. One example is from the examples that we studied. So, so maybe I should mention this example. I remind you of this example. In some sense, this is a non-example. But anyway, what is the idea? The idea is that, well, the Lie algebra SU2 is isomorphic to the Lie algebra SO3. Okay. And in fact, we use this isomorphism of Lie algebras to show that there was this group homomorphism from SU2, the group SU2 to SO3R. Yeah. So now, well, we knew that this map is 2 to 1, right? And in fact, these two groups are not isomorphic, SU2 and SO3R. You can show without much difficulty. For example, by comparing the size of the center. You see, like the center of one is like 2 elements, the other one is something else, okay? The size of the center, you can check that these two groups cannot be isomorphic. All right? Even though their Lie algebras are isomorphic. And the reason is that even though this guy is simply connected, this guy is not simply connected. Okay? Is it clear? Maybe I should just add non-example here. Okay, so now I'd like to come back to this formula and explain to you how this BCH formula is proved. Okay. So let me just write that formula again. then maybe I should write here. So back to the BCH theorem. So what is the formula? The formula is that we have this log e to the x, e to the y equals x plus integral from 0 to 1 g e to the add x e to the add y e to the t add y y dt. Okay. So this is the formula. And for some g, what is g? G is really this power series. It is like log z divided by 1 minus 1 over z, which you can expand as sigma negative 1 to the power k over k plus 1 z minus 1 to the power k z. Which you can also write as a power series in z minus 1. Okay. So the proof is a little bit technical. So be prepared for some technicality. I don't expect you to memorize such technicality. But the technicality is useful in some sense to sort of, so first of all, it's like see the ideas of some, celebrated theorems. And second is that there are also some interesting things that are counterintuitive that show up there. So maybe, I would like to sort of point to them. The first thing that's actually counterintuitive is the following. So maybe I should start by the following example. Suppose I want to differentiate and this is the calculus question, e to the x plus ty at t equal to 0. So x and y are fixed numbers. So you should be able to do this. What's this derivative? That's right. It's e to the x times y or y to the x, right? Okay. It's just an example of a chain rule, right? Okay. However, what if I wanted to differentiate the following? What about the following? And I stated as a sort of assertion, a theorem. The derivative of e to the x plus ty at t equal to 0 for x and y n by n matrices. Maybe I just write here. What is this? Do you think it's given by the same formula? This is calculus, yeah? So a priori, there's some ambiguity when if you think about it. So what would you like me to write? So maybe you should tell me what you would like. It's okay if you say the wrong answer. The first time I looked at also gave the wrong answer, but what would you like me to write? Just e to the xy? Yeah. Maybe it should be like that, huh? But already there is ambiguity because you could maybe write it as y to the x, but they are not the same because x and y do not necessarily commute. So it's not clear which one we should write. Why should we write y on the right? Okay. So then we have to differentiate this properly. Okay. And in fact, these answers, they're both false. They're not correct. Okay. The reason is, okay, so you might say, okay, what's happening with the chain rule? I could first differentiate the exponential function, and then I should differentiate x plus ty. The derivative of x plus ty can't go wrong. That's just why. What about the derivative of the exponential function? The problem is that the exponential function in matrices, has derivative 1 at identity, but in general, it doesn't behave like the usual exponential. And to see this better, maybe we could just write the power series to convince ourselves of this fact. So let's write the power series. So what is this power series for e to the x plus ty? So this is going to be 1 plus x plus ty plus 1/2 x plus ty squared plus some other terms. Let's now expand and differentiate. So this is 1 plus x plus ty plus 1/2 x squared plus 1/2 t squared y squared plus 1/2 txy plus tyx and so on. The other terms, yeah, okay. So now let's differentiate with respect to t. That already shows what's happening. So if we differentiate with respect to t and set t equal to 0, well, these are constants, they will disappear. So you get this y. And then here you get a 0 for this one because you're the 2t survives, the t survives. And here you end up with this xy plus yx. All right. So it looks like you're getting both the y on the left-hand side and on the right-hand side. So neither this formula x e to the y, like y e to the x, or nor e to the xy would be correct. You should have some formula that puts somehow x and y on both sides. Okay. All right. So then now let's see what, I mean, this is now a calculus question, but it's not an easy calculus question. Calculus can be hard, right? So then let's see what the answer is. So the answer is the following. So it is e to the x times 1 minus e to the minus add x divided by add x. So I write it like this, and I'll explain what this means. Of y. So e to the add x is clear. I mean, by e to the add x, this is just like 1 plus add x divided by 2 plus 1. Like just repeat add x. Okay. What does division by add x mean here? Can you explain? How can I divide by some linear transformation? What do I mean by that? What could I possibly mean? So what I'm doing is, so this is important in terms of understanding such formal calculations. What I'm doing is, so I would like to do identity minus e to the t minus t divided by t. Okay, so I want to do this. Okay, t is not necessarily invertible, so I cannot quite write this. If t was invertible, then that's what I meant. But who knows if t is invertible or not? T can be even 0, right? But still, what I can do is I can write the Taylor series of the numerator and see if it's divisible by t. Okay, so this is like, so 1 minus e to the minus z is 1 minus 1 minus z plus z squared over 2 minus z cubed over 6 blah plus minus. And now you see that the 1 and the minus 1 cancel out, so you end up with something from which you can factor a z. And now you can divide by z without any harm. All right. So this means that I'm actually using the following formula. So maybe I erase all of this after I explain what's happening. And now here I'm using the following. So here, 1 minus e to the minus z divided by z is just 1 minus z over 1 factorial plus z squared over 2 factorial minus z cubed over 3 factorial plus minus. Okay. All is good. All right. So now at this right-hand side, this expression makes sense because that's some series in add, in like add or add, like powers of add of add or add of add of add. It's some linear transformation. I apply it to y. Okay. Basically, it's just some brackets. So in explicit form, in other words, using this series for 1 minus e to the minus c divided by z, I can write that the left-hand side of this guy is equal to, well, there is an e to the x to factor out, as you see on the right-hand side right here. So I factor this out. And then I write that what is left from that series. It will eventually be 1 minus xy over 2 factor over 1 factor. Yeah, it's 1 factorial, 2 factorial. Sorry, the first term is for the 1 factorial. It's right here. But then I have a. Maybe I made a mistake in these denominators. Okay, sorry, I made a mistake in the denominators. Okay, I think the denominators should be 2 factorial. Yeah, 2 factorial, 3 factorial, 4 factorial. Yeah, I misread what I had written here. Okay. So then plus x xy over 3 factorial minus plus, like this. Okay. So as I mentioned, this z is being replaced by add x. But what is add x of y? This is just xy. And if I do add x to square of y, it will be x xy, and so on and so on. Yeah.
I guess we've not seen exponentials of operators before, but are these, it's like add x just being viewed as a matrix itself, I guess, and that's why.
Well, you have seen exponential operators. I mean, we talked about e to the t for a matrix t, right? Now add x, it's some linear transformation from the Lie algebra to itself.
Okay.
So it is some matrix of some size. The size will be dimension of G.
Yeah.
It's some big matrix. But anyway, this does not depend on the matrix representation. So e to the t for a linear transformation t can be computed when you choose a matrix representation of t, but it is just some linear transformation on the vector space on which t acts. Okay, thanks for asking. Is it clear? Okay. So basically, the right-hand side really is a linear transformation on the vector space G, the Lie algebra, right? As it should be, because this exponential on the left is also some map from G to G, right? This is how we should understand it, as e to the x. Well, I mean, there's okay. So I wasn't very precise. So the add part of it is a linear transformation on the Lie algebra. But anyway, this is even not about a general Lie algebra. This is just about 2n by n matrices. It's just about the Lie algebra of all matrices. The exponential part is e to the x is not a map on the Lie algebra, but let's just not worry about that sort of intrinsic interpretation. This is just some relation about matrices, and add x on matrices is just the usual for the the adjoint for the Lie algebra GLN. Okay. All right. So maybe I should add it. So here, add x goes from MNC to MNC. It takes any y to add x, like add x y, which is okay. All right, maybe this bit was not clear. Now, hopefully it's more transparent what I'm saying. Okay. All right, so how do we prove this assertion? The right-hand side, as we see, it is not what we expected from like naively thinking about chain rule. Chain rule was not applied correctly, so now the formula looks different. How do we prove such a thing? So the proof is also a little bit of a trick. I mean, there are various ways to prove this, but for the moment, let's just use this trick. So the trick is that you interpret this series as some integral. Okay. So first I have this lemma. So the lemma is that let Z be any linear transformation. Be any, I don't know, be an n by n matrix. Okay, so then the following limit, the limit of the following sum, which is identity plus e to the minus z divided by m plus e to the minus 2z divided by m plus da 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 plus e to the minus m minus 1 z divided by m. So there are m terms in the summation, and they're like e to the minus k divided by m is equal to e to the, 1 minus e to the minus c over c, where the right-hand side, again, is interpreted as like the series, okay? So how do we prove this lemma? So the proof is that, in fact, this summation, I missed the factor of 1 over m, sorry, this 1 over m, so this summation is a Riemann sum of some integral. Okay, so left-hand side, so in this argument of limit, is a Riemann sum for this integral. So what would be the argument of the integral? Can you guess? I'm subdividing the interval from 0 to 1 into m parts, and I'm evaluating the function at those values, right? This is like a Riemann sum, right? You remember what the Riemann sum is for an integral? So you take this, then you make these rectangles, and then the area under the graph is just the sum of the areas of the rectangles. And what is the rectangle? Like this is like 1 over m, because the interval is from 0 to 1. I'm subdividing into m equal parts, and the height is the value of the function. F of 1 over m, f of 2 over m, something like this. So what is the function then? Exactly, it's e to the minus tz. Right. Okay, so it's the Riemann sum of this integral. Therefore, the limit should be just the value of this integral, this matrix integral. And how do you interpret a matrix integral? Well, each entry is a function of t. So even this z is an n by n matrix, this e to the minus tz, each entry is some function of t. So I'm integrating entry-wise. Okay? But now, in fact, this is how you can do this. Okay, so now this is equal to, so the claim is this is just the right-hand side. This is identity minus e to the minus z divided by z. How can I do this so quickly? Well, first, if I had just a 1 by 1 matrix, which means just a number, this was just some calculus question, right? So for z, a number, this is just, you just compute the antiderivative of the exponential. This is again exponential divided by t or something here, okay? So it will be just e to the z minus 1 divided by z, okay? This is just calculus. This is like, I don't know, first year calculus. Okay? So now I would like to have this relation for a general matrix. Then what do I do? From this calculus, this 1 by 1 matrix thing, how can I get the result for a general matrix? What trick can I use without doing any work? I want to prove this without doing any heavy duty work. So I want to use some clever idea. Okay, so I'm assuming that I know this. I want to prove this for an n by n matrix. If the matrix was diagonal, then the exponentials would look very simple, and it would be true, right? So now, for diagonal matrix, so for z diagonal, so e to the minus tz will look like, so if z is like this matrix, like maybe z1, zn, then this is like the matrix e to the minus tz1, e to the minus tzn. And the integration passes to the entries, which are just like now reduces to the one variable case. Okay? So it immediately reduces to the number. Okay? So for diagonal matrices, this was like easy. Is it clear? Is it convincing? Do you want me to explain more? Should I explain more? Are you happy? Should I explain more? Okay, it's good. All right. So now, what about the general matrix? So I did it for diagonal matrices. Now, what do I do next? Exactly. So now that I have it for diagonal matrices, I can also do this for diagonalizable matrices, matrices that after conjugation become diagonal. Why? Because if I do if I conjugate this, then I get e to the minus t conjugate of this. And the right-hand side is the same story, right? So, I mean, if I just conjugate I minus e to the minus z over z, then I get 1 minus e to the minus pz p inverse divided by pz p inverse. Okay? Remember, the right-hand side is a series. Every term is conjugated in that series. Therefore, by conjugation, I can make my matrix diagonal if it is diagonal. So this proves, this implies, the assertion holds also for Z diagonalizable. And now for general matrices, well, I want to have this integral relation for a general matrix Z. What I do is I converge to that matrix by diagonalizable matrices, which I can always do, right? We have discussed this. Every matrix is a limit of diagonalizable matrices. This is an important fact. We have talked about it, right? Did I mention this? I think we did. We did use this fact at some point. Okay. So now the integral value on the left, it's like, basically the functions e to the minus tz, they will converge to your desired function for the z, which might not be diagonalizable. And same for the right-hand side. Both sides converge. All right. So now, so we could say is that since diagonalizable matrices are dense in M and C, the lemma also holds for all n by n matrices. I mean, using a standard convergence argument. Okay. All right. So now I prove this integral formula. I mean, this, I'm sorry, I proved this Riemann sum limit. Now I want to use this to differentiate e to the t plus, e to the x plus ty. All right. So back to the differentiation, which means the proof of that theorem. Not the VCH theorem, but just the derivative theorem. So here now I use another trick. The trick is to use the Lie product formula. So, or rather the idea of the Lie product formula. So I write this e to the x plus ty as e to the x over m plus ty over m to the power m. Okay? And now, well, what am I interested in? I'm interested in the derivative of e to the x plus ty at t equal to 0. Okay. Now, in principle, you should think about it as computing the derivative of the exponential function as a multivariable function in the direction of y. Okay, so maybe I should also like give this insight. So this is directional derivative of exp. Okay? So it's at point x, you have the direction in y, you're differentiating in this direction. This would be like x plus ty, right? As t goes to 0, right? And now, you know from calculus again that the partial derivative is linear in the direction, right? So, in other words, if you want to compute the derivative, if you want to compute the derivative of a function, multivariable function in the direction of v at some point, if you write this as a linear combination of the standard basis, then this is equal to v1 d dx1 f plus up to vn d dxn f. This is calculus again, right? The derivative is linear. The directional derivative is linear in the direction. All right? So now what this means is that, in fact, this delta is linear in y. Okay? Okay? All right, so now let's use this expansion to compute the derivative. If you want to compute the derivative, now I have expressed e to the x plus ty as a product of m functions. If I wanted to differentiate with respect to t, I could use the Leibniz rule for the product to differentiate each term, right? I mean, I differentiate one of the terms and multiply by the other terms. They go on both ways. Looks like I made my problem harder by reducing a derivative with respect to one function to like m functions. But in fact, it turns out to be useful. So what I have is I have d dt e to the x plus ty. It is the derivative. So I'm doing this at t equal to 0, right? So it's the derivative of e to the x over m plus t y over m to the power m at t equal to 0. And now this is really a product of m functions multiplied. If I want to differentiate this for each k, I should differentiate the kth one, evaluate the derivative, and also evaluate the ones before and after at the point I'm differentiating, which would be t equal to 0, and then multiply everything, right? So what I get is the following summation. I get the sigma k starting from 0 to m minus 1, because there are m terms that I should differentiate one by one. And then I get, before the guy that's differentiated, I just have this e to the x over m plus ty over m k times, but I have to set t equal to 0. So I basically get e to the k x over m. Or maybe I have ordered my indices like in the opposite direction. Maybe I just write m minus k minus 1. Right, okay. I'm just like, I shifted my indices. Instead of k, I wrote m minus k, basically. Then I have the derivative of the middle term, which is e to the x over m plus t y over m at t equal to 0. Still, I don't know what it is, right? I'm just like in the same problem. And after that, I have e to the k x over m. Okay? Now, what is this middle guy in terms of what I had here? So here I had this delta xy defined as such, and that middle guy is going to be just delta x over m y over m, right? So what I get is sigma. Well, here I also have an e to the m minus 1x that can be factored out. So let's factor this out. So e to the m minus 1x. Should I divide by m? I think I missed the division by m, sorry. Yeah, okay. Then I have the summation, which will give me e to the minus kx over m And this term is delta of x over m, y over m by definition. And then I have e to the k over m, kx over m. All right. But remember that the directional derivative was linear in the second argument, the direction, right? So I could factor out the 1 over m. So I could write this as e to the m minus 1 x over m, 1 over m, e to the minus kx over m, delta x y over m, e to the kx over m. Okay, so now I have a conjugation by some exponential, right? Remember another formula. So e to the tx y e to the, or rather, I mean, I don't have to have like a t in it. So I mean, first, like maybe I just write the formula on the side. So e to the a, oops, wrong color. So e to the a b, e to the minus a. What is this? You had a formula for it, right? Okay, am I giving the right formula? Yeah, so this is basically this is add e to the a, so maybe I write it. This is add e to the a b. Okay, now you see that this is a matrix formula, but thinking about it using Lie group's ideas can simplify life. Okay, which is the same thing as e to the add a b, because the derivative of the capital add action is the linear add action, the Lie algebra add action, which means this is b plus ab. Maybe I write it here. It's like b plus ab plus 1/2 aab plus so on and so forth. All right. So now I have something similar, e to the some, like some conjugation by some e to the a thing, where a is like really this guy. Maybe I can remove this, okay? So I can use the same trick to rewrite this, okay? So by using that, what I get is, well, the e to the m minus 1 over m x will survive, but the summation, so I have this 1 over m, and then I should write the exponential of minus add x over m to the power k. I mean, I could think about this as e to the k over m to the power k, right? And this is this exponential. All right, I don't know how I changed my color at the moment, but anyway, it just, all right, okay. And then I have this delta of x over m comma y. Okay. So now remember that now I got some extra thing which I don't know how to remove. Do I know how to remove this? No. Okay, maybe the solution would be to stop one node and then open it again. Okay. Okay, so now, well, let's look at this. So now we wanted to compute this derivative at t equal to 0, and we broke it into these steps. Now, when m goes to infinity, okay? So as m goes to infinity, we could like let m go to infinity. We can take m sufficient, like larger and larger, and see what this is. So the following happened. The first thing is that this e to the m minus 1 over mx will converge to e to the x. Okay? And the second thing is that here I have this summation. This is the same summation as the lemma with the operator z being this e to the minus add x over m. As you can see, if you come back here, maybe I should, okay, so if you look at this formula, this Riemann sum, so if I set z equal to minus add x, not 0 minus over m, but just z equals like minus add x, like add x. Okay, so I would like to set z equals to add x. All right. Then I get the same thing, right? I mean, forget about this part. First, think about this as an operator, which is some matrix in some big space. All right. It's still finite dimensional. So this is the lemma, okay? So maybe right here, we can use the lemma. So as m goes to infinity by the lemma, so this converges. Maybe I just right here. So here as, maybe here as m goes to infinity, the first thing converges to e to the, or maybe I just need two more space. So maybe, okay. Sorry for changing this. So as m goes to infinity, I just want to create more space for what I want to write. So this thing above, it converges. First, this exponential factor outside converges to e to the x. Then this 1 over m times blah, blah, forgetting this part. If you forget this part, you have the lemma. So maybe I just write a lemma. So use lemma for z equals add x. Then you end up with the right-hand side of the lemma, which is 1 minus e to the minus z, but that z was now this add x divided by z, which is add x. And this delta x over my, this delta x over my, this also converges to delta 0y. Maybe I just, okay, maybe I write it in a different color. Why is that so? Because this is the derivative of some function at x over m. But that function is really like infinitely times differentiable. So the derivative is a continuous function. The directional derivative in the direction of y is continuous in the argument of the function, which is the x over m. Right? Oops. Okay, so now here, instead of this delta x over y, in the limit, I could just put delta 0y, which is just y. If you come back to the definition, what is delta 0y? This means now I can set x equal to 0. This is just a derivative of the exponential function. It's the identity map, which is evaluated at y, so it's just y. All right, so now I can also replace this by y. Oops, wrong color. Okay, and this is the right-hand side of the theorem that I want. So I started from the derivative of e to the x plus ty, and I just got the right-hand side I want. Okay. So this was rather sort of delicate calculation, but there were several ideas in between. So I think it was useful to do this calculation, to learn how one can deal with such matrix. But how should one do matrix calculus? It cannot, it's sometimes non-trivial, and there are many interesting ideas. Okay. Were the ideas clear? Okay. All right, now finally we come to the proof of the BCH formula. All right. So now, did I have the BCH formula in the beginning of today's lecture? So let me just show it to you. Here. Finally, I want to prove this formula. Okay. Any questions about whatever I said so far? Because I'm going to sort of change gears a bit. Everybody's happy? Following? Yeah.
Conceptually, what was the point of introducing the m and the limit taking the limits? Like, would it not have been possible without introducing the m with a key part of the proof?
Yeah, it is possible. That the idea was that we can think about this yeah, this is not the only proof. I mean, you could probably do something in, like, if you think about the derivative as linear maps, you know, linear maps of linear maps and so on, then you could also do this. But then you'd need to somehow imagine the derivatives of such big things. Okay, so yes, it's possible. But if you have done calculus on manifolds ever, you know that it can be very hard to sort of set things, you know, set even the notation and write things down. Once you can do this, then everything becomes elementary. But conceptually, it becomes sort of, you know, the sort of imagining the higher dimensional things can be the complication. This somehow simplifies. This is a trick to circumvent some complication. But yes, you could do this, and you don't have to really go in this direction. There are some other, you know, maybe more sort of brute force, but sort of more straightforward. But there's more work to do, I mean, computationally. But I mean, but you have to really write this derivative as a linear map on the right spaces and then write some complicated chain rule and so on. So yes, it's possible, but this is kind of more quick. All right, so now back to here. Any other questions? Okay. So now back to here, we want to prove this assertion. Basically, we want to write this e to the x to the y as log of, like e to the z for some z, right? So what is the idea? So the idea is the following. Again, you remember at some point when we wanted to prove the BCH formula and like use, basically you want to prove the BCH formula for the Heisenberg group, we introduced some parameter t, right? And that was kind of, it seemed like a redundant parameter introducing first, but it helped us because then we got our formula by some differentiation and evaluating at 0. So we want to repeat the same trick, okay, by introducing some extra parameter. All right. So remember, we are interested in this log of e to the x e to the y, and I would like to now consider, so make a proof of the BCH theorem. So I want to define z as a function of t. So it's a matrix valued function of the parameter t, which describes the logarithm of e to the x times e to the ty. So it's well defined for x and y small, okay? So here, so for x and y of a small norm. I mean, you really don't need to assume norm of y is small. You can make t small. Okay, and maybe I should say and t is small. But really, eventually, you want to set t equal to 1. So, okay, maybe you do need the assumption that y is a small in norm. Because otherwise, you might only define this z of t for some small neighborhood, some small interval t. But anyway, so for x and y small norm, log of e to the x e to the dy makes sense because that lies within a small distance from the identity element of your Lie group, okay? Or in general, like the matrix. I mean, everything is really happening in matrices, right? Because we are in a matrix Lie group. So this is really a relation about matrices. We're proving something about two matrices x and y. Okay? So I define it as such, and I want to compute z of 1. Right? Okay, so we are interested. Okay, so now we want to massage this a little bit and compute z of 1 as some integral of the derivative of z of 1, to be precise. Okay. All right, so how do we do this? So, so we have, first of all, that e to the minus x equals, or maybe e to the minus x times e to the z of t equals e to the ty. And now, by differentiating with respect to t, well, the e to the minus x is constant, right? So I get e to the minus x times the derivative of e to the zt. It's equal to the derivative of right-hand side. Well, I'm doing differentiation at t equal to... Well, okay, here I don't want to specify t equal to 0. It's just a general t. It still makes sense for any t. So at t equal to t0, really, I mean, sort of thing. So on the right-hand side, I get e to the ty times y. I mean, I don't run into issue on the right-hand side. It's just a derivative of the power series. There is no x and y non-commuting to lead to a problem like the x plus ty. All right. So then, so now I can now write the derivative of this exponential as in terms of e to the x and e to the ty. So then d dt e to the zt is e to the x, e to the ty, y. Okay? But e to the z, e to the ty is just e to the zt by definition, right? All right? And this means now I can isolate y in some sense, put all the zt's on one side. So I could write this as e to the minus zt d dt e to the zt equals y. Okay? So this shouldn't surprise you in some sense. So this is some analog of this formula. I mean, this formula f prime divided by ft, which is log of ft prime. Okay? It's some analog of this, but we have some non-commutative things going on. But you have seen this formula, I hope. So this is calculus again. All right. So then, but now, from the previous theorem, so maybe this is one step, okay? So we have this. So this is step 1. And how much time do we have? Okay, we have a few more minutes. Hopefully we can manage to finish. So now step 2 is that by the theorem, we can also interpret the left-hand side slightly differently because it's the derivative of the same function that we had. So basically, so we have this e to the minus zt d dt e to the zt. This is just 1 minus e to the minus add zt divided by zt. Again, interpreted by the formal series of dz dt. Okay, so I mean, previously we had this exponential on this side in the theorem. Okay. Okay. But now, well, we have calculated this above and it's equal to y. So now step 3 is an immediate consequence of the previous step. So 1 minus e to the minus add zt divided by zt dz dt is y, okay? And if you remember the series for this guy, this series had a constant term, non-zero constant term, like 1 minus e to the minus z divided by z. It started from 1, right? If you go up here, you see the series starts from 1. So this means that if you put some small matrix there, the series will be an invertible matrix, because this tail of the series cannot have large norm. So I have one identity minus a small matrix. It cannot be, it should be invertible, okay? And therefore, I can now invert this whole thing here. I can compute the inverse of this, all right? In other words, it follows that dz dt is 1 minus e to the minus add zt over zt dz dt. I'm sorry, y. So there's an inverse and then y. So I'm just like, this is a like linear transformation applied to some vector, yeah, right? I'm applying the inverse to both sides. So here on the left-hand side, the dz dt survives, and on the right-hand side, I have to apply this series in zt to the function y, to the vector y, which is a fixed vector, okay? And now here, the right-hand side, I can write as so this is a little bit sort of, again, tricky. So this is 1 minus e to the add x, e to the t add y, inverse divided by log of e to the add x, e to the t add y. The whole thing inverse applied to y. Yeah. Oh, what happened to the screen? Why is it gone? Okay. All right, now we can see this. So what is happening here? Well, first of all, by the definition of zt, this is just log of this. Okay. Now, what about the numerator? In the numerator, the point is that, so e to the zt, or e to the add zt, it is e to the zt y e to the minus zt in principle. Okay, so if this is applied to y, that's what it is. Okay, but then e to the zt was this e to the add x e to the t add y. All right. Or maybe I should say e to the I mean e to the x e to the t e to the ty. Right. Okay. And so now you can think about this as conjugation by this. So this is conjugation, e to the minus ty e to the minus x, which is really e to the add x e to the t add y applied to y. Okay, so it's all a consequence of that relation, this green relation. Okay, so you see this relation can be very important. It was not a trivial relation in the beginning. It was kind of, you know, not immediately obvious how to thought to see this. It was really a consequence of Lie theory, and you see how it can be useful, okay? So now when we get there, what do? So now we see that, in fact, the derivative of this dz is expressed as some function depending only on t, okay? So this means this is exactly what we wanted. So hence, maybe this is now, we had step 3, now it's step 4. From the previous step, we see that this dz dt, it is just g of, well, this e to the, I mean, you see this right-hand side is just a function of e to the add x, e to the t add y, right? So this is g of e to the add x, e to the t add y for g of z being 1 minus e to the minus z divided by z. Okay, this is applied to y. Okay. Actually, I have some inverse. Do I have some inverse? Yeah. Sorry. No. I just wrote it incorrectly. So this is not the function. The function is different. So this is for so this is 1 minus z inverse divided by log z. Okay. And now, well, we are interested in z of 1. So this is going to be z of 0 plus the integral of g e to the add x e to the t add y dt. This is again first, like this is the fundamental theorem of calculus. Yeah.
Still missing inverse for g of z equals this inverse.
There's an inverse missing. You're totally right. I'm missing this inverse. Yeah. Okay. And all right. So now, okay. So now I got to this formula, and all right. So maybe we can stop here. So basically, this is what I wanted. Okay. All right. So now, okay. So we're almost there. So next time I'll just explain the last bit. Okay, but we're technically done. I mean, z of 0, we can evaluate and so on and so forth. You just have to match the z with the other, like the g with the other g. Okay. But we're running out of time, so maybe I just stop now. So next time, we will talk about simply connected Lie groups, and we will see an example of a Lie group which does not have a simply connected cover, which is a matrix Lie group. Therefore, it turns out in order to construct simply connected Lie groups associated with Lie algebras, we really have to step outside the convenience of the comfort zone of the matrix Lie groups. Okay, but that will be a very important step because this leads to a non-matrix Lie group, which is of fundamental importance in quantum mechanics. That's the universal cover of SL2R, which is related to the quantum harmonic oscillator model and so on. Okay, so we stop here. We continue. Now on Wednesday, we have our midterm exam. So we will continue this on Monday, the following Monday. But on Wednesday, there's the midterm, which will take place right here. For those who are taking the course virtually, they will receive the exam as an assignment on Moodle.